Last topic of Module 2, Part E, brute force method. Yeah. The reason we have 5 parts, remember, we use 1 part for quiz number 1. Yeah. And after today's lecture, we complete Module 2, so you can expect our quiz number 2 will start at this weekend. Yeah. So I try to create it sometime tomorrow, yeah, and post it, yeah, probably a night, late night. So you can start to work with more than 1 week, yeah, just as the quiz number 1. Okay, all right, so let's do our last topic, brute force method. I mentioned this brute force method a little bit in our polynomial evaluation problem today. So let's learn this topic another time with a little more information. E.1, Introduction to Brute Force Method. First, a description of brute force method. I like to describe some properties of a typical brute force method. Usually there is no clear definition for that. So people say in that way, because based on the usual understanding, people can understand the meaning of this brute force method from its name easily. Properties, the first one, it's a straightforward approach. You just solve, here we're talking about a computing problem. You solve a computing problem without using any special techniques. Now, if you use some special techniques, so then people may not treat it as brute force, okay? Or with the minimum advanced knowledge. You can use the knowledge that everybody knows. Everybody here, I mean, in our field, in our CS field, CS basic CS training. Okay, yeah. All right, you can always apply it to a problem. Given any computing problem, without using any special technique, you don't worry about the efficiency. You don't worry about the performance. You only want to get a correct answer. So you can always apply the brute force method on a computing problem. In general, it is not the best algorithm. All right, yeah, in general, for here, I like to say for non-trivial problems, okay, yeah. So here, let's say, yeah, for non-trivial problems, okay, for trivial problems, you can get the best solution, yeah. It is usually used as the starting point for more advanced algorithms. Here, I remember I talked about this point before. Because when we have a relatively hard computing problem, at the beginning, we do not have any idea how to get started. Most people have this kind of feeling, okay? At the beginning, we do not have any idea how to get started, okay? Yeah. Then, in order to get started, some experienced problem solvers. Now here, let me use the problem solvers. They like to start with this brute force method.
We just want to find the solution first. All right. This procedure can help us understand the problem a little better. So when we work on it, when we, get our hands on this problem, so we can understand better and better. So that's the point. We know this could not give us a good solution. We do not expect the best solution, but even not a good solution. Okay, yeah. The efficiency difference between the brute force method and more advanced algorithm could be huge. Yeah. This is from the experience. Yeah. From our polynomial problem. So we have seen this point from the polynomial problem. Here at this point, you have our programming project number 1. Okay, so you need to do experiments on 3 different algorithms. In that way, you will have your own experience. Because before you do the programming, you just heard from my explanation. I told you, the difference is big. But now you have a chance to do experiments by yourself. Let you feel about the huge difference. Yeah. All right. Yeah, so the polynomial evaluation problem. Yeah. In that one, method 1, I try to, so when you do experiments, the method 1, remember, I ask you to, do experiment with the size approximately around 200,000, not 20, 200,000, around this one. Yeah. This one, then the response time, you need to expect response time. Approximately 30 seconds. 30 seconds. Yeah. Yeah. So, because if you do not have oh, sorry. So I have this. Sorry, I forgot to turn off my cell phone. Yeah, so let me turn off now. Yeah. Yeah. Let me just put on airplane mode. Yeah. Airplane mode. All right, good. Yeah. Because here I let you know first, you may need to wait about 30 seconds because it is so long. When you sit there waiting for the response for 30 seconds, that's really long. And if you do not know this ahead of time, you may need to wait 30 seconds. If you do not know this fact, you may feel something is wrong. What's wrong with it? When I run the program, I couldn't get anything. Because when you sit there waiting for the response 30 seconds, feels like century. Yeah. But here I tell you the fact, so you can prepare mentally. Yeah. So that is normal. That is quite normal. Yeah. All right. Yeah. Next. Now we need to work on some concrete problem to see, this brute force method. So let's apply it to another computing problem. Yeah. That's not a new problem. Our old problem, problem number 4, sort and array. So here we revisit it. Yeah. The problem, so we're familiar with this problem. Let us solve it in a different way. Okay, different way, second way. The first time we solve it using that selection sort, all right? Here, we want to take a different way. But you may have this question, why we need to solve it another time, right? So usually, think about your own experience. If you already have some solution on a particular problem, usually most of the people, they do not bother to find a different solution, right? Yeah. They feel it's done. Okay, why? Yeah, but here, in this class, for this particular problem, sort and array, number 4, we will solve it many, many times. Yeah. About 6 or 7 times, that many. Yeah, so we will do at least 6 times, that many times, 6 different solutions. Yeah. Why we solve the same problem so many different times? So here, let me explain in this way. Yeah. Okay. Yeah. Our view, we take this view. All right. So a problem is a carrier of a set of thinking methods that result in different solutions. Here, let me explain in this way. What is our goal? Yeah. Our goal, we want to learn here. If I write a goal, we want to learn problem solving techniques, right? That's our goal, right? Our main goal for this class. Yeah. Problem solving techniques for computing problems, right? So think about it. Those techniques, their methods, their special ways, each one has one specific procedure, right? Step-by-step procedure or algorithm. We can call it algorithm. So each one has its own algorithm. But the question is, those algorithms mainly, so it is a thinking way, right? It is a thinking way. It is a not concrete object, right? It's not a concrete object, so you cannot grab it. Okay, it's not concrete object. It's a thinking way in your brain, something in your brain. Okay, yeah. So the question, how to carry those different thinking ways for our future problem solving? Yeah, because in our future real world problem solving, we need many algorithms. We need to use many tools. And these algorithms, we will use them as tools to solve real world computing problems. Yeah. But you need some carrier, right? You need some container. Yeah. You need to put these thinking ways, methods, algorithms, techniques in some container. Yeah. Holding these, thinking methods. Okay. Yeah. All right. Yeah. So we treat each computing problem as this carrier. Here, our sorting problem. Here, sorting. Our sorting problem is that carrier. And for this class, we need to solve this sorting problem 6 times. So that means the sorting problem carries 6 different algorithms. That's the special view we take. Okay, yeah, all right. The thinking methods are important to help us solve other problems. No. Because after we learn these 6 algorithms, they belong to our experience, right? These 6 algorithms, they belong to our experience. And then later, in our real world applications, we have this experience. So when we have a new computing problem, so this kind of experience could be helpful for us to find a solution for a new real world computing problem. So that's the value of all these methods. Okay, yeah, all right, yeah. A view based on special property. Now we need to solve this sorting problem in our second time. Yeah. Although I call it second time, but actually you did it before. This problem, yeah, you will see later, you solve it before in your CS3130SP23Module2EVideoAll. Yeah. Because I taught this class once before. Yeah. I taught this one. Yeah, so you will see it. All right. Yeah. Observation. Yeah. First, we need to find some special property. Yeah. Okay. You need to really do some good observation on your current computing problem. Try to discover some special property. Then your solution, you need to take advantage of this property. Okay, yeah. When we do observation, we need to find, because you may find many different properties. You may find many different properties. Okay, yeah. So for one solution here, we want to focus on one special property. Okay, all right. So let's look at that property. Yeah. Here, I just draw a simple diagram. Yeah. Using this diagram, we try to visually discover some special property. Okay, yeah. All right, so let's look at 2 pair of elements. Here, I use, this 2 arrows point to 2 elements. Yeah. All right, so think about when we sort all the elements in this array, what is the special property related to the order of these 2 elements? Order, so order information. Order, ascending order. We mean ascending order. Our default order meaning is ascending order, not descending order. Descending, not the default. So you have to say descending if you refer to descending. But for ascending, we do not need to say ascending. Just order. It is ordered, then ascending order. Okay, all right. But here the question is, if these 2 elements out of order, not in order, out of order, okay, what would happen? Out of order, in order, out of order. Yeah. So you know the meaning, right? Yeah. So here, that's the property we want to discover. the critical property, if the array is not sorted. Yeah, we make this assumption. Yeah, array not sorted. Assumption. Okay. Yeah. Then there must be two adjacent elements. Here, adjacent. Yeah. Here, I look at two adjacent elements. Okay. Then there must be two adjacent elements that are out of order. This is the property we discovered. Okay. Can you understand this? Can you imagine, see this fact? Yeah. When I pointed it out, yeah, because you're thinking this way. If that is false, okay, so we use, so what's that? Contrapositive method, right? If it is false, that means any pair of adjacent elements are in order, okay? Any pair of adjacent elements are in order, then the array must be sorted, right? Well, think in this way. If this statement is not true, then we can say in this way, if any pair of adjacent elements are in order, yeah, in order, because we want to do the negation, right? We want to do that, the negation of this, conclusion part, negation, okay? Yeah. If any two adjacent elements are in order, then the whole array must be sorted. Yeah, so we see that, we can see that, all right? But here we have assumption the array is not sorted. That means your claim is false. Your claim, and that claim is, any pair of adjacent elements are in order. That is false. If that is false, then there must be one pair of adjacent elements that are out of order. Okay? They're out of order. Yeah. All right. So now, if we have this property, then we will just design an algorithm working on this property, targeting on this property. Okay? Yeah. All right. Yeah. Here I give you the reference on our textbook. Yeah. All right. Okay. Then to get it solved, in order to facilitate our discussion, here we need to use a concept. Yeah. Concept, inversion concept. Because if we give a formal description of this important concept, then when we do discussion, it is much easier. Because we do not need to say a lot of words. Okay? Yeah, inversion. All right. A pair of elements here, I look at a general pair of elements. Yeah. A sub I and A sub j is called an inversion if the subscripts I less than j, but the values, element values, A sub I is greater than A sub j. So that's called inversion. Yeah. So why inversion? Because you look at the directions of the inequality signs, opposite, right? Not in the same direction, in opposite direction. Okay. When that happens, so we call this pair of elements, they form an inversion in this array. And you can understand why we need this concept, because this concept just describes that out of order phenomena, okay? Out of order state, okay? Yep. So we want to discuss based on out of order phenomena, okay? Yeah. So we use this inversion concept for the discussion, okay? All right, yeah. After that, so then let us change the wording in our discussion. Let us use the inversion concept in our discussion from now on, okay? Yeah, all right. Now, yeah, so let us write this property another time, okay? Yeah. This time we will use the inversion concept, okay? If the array is not solid, there must be an inversion. All right, so here, this second one is different from the above one. Yeah, so the second one, I just want to say related, but not necessarily the same, okay? Just related. Yeah. Not the same, okay? Why not the same? Because in the above, we mentioned the adjacent element. Here, we do not, we just say arbitrary inversion, right? Yeah. Because in our definition of the inversion, I, J, not necessarily adjacent, right? Not necessary adjacent. Yeah. So here the meaning is different. Okay. Yeah. So we have this, you know, slightly different property, slightly different from the above. So if the array is not solid, there must be an inversion. It's also correct. Okay, there must be inversion. Otherwise, think about it. If there is no inversion, thinking this way, if there is no inversion in a given array, no inversion, okay, then the array must be solid. So, can you see that? If no inversion, then array solid. Okay, array solid. Yeah, because no inversion. Yeah. Okay. All elements must be in ascending order. That corresponds to no inversion case. Okay. Yeah. Because if you can find one inversion in the array, then the array, the elements in this array won't be in ascending order, right? Just, you need some intuition here, okay? You need some intuition, yeah, to get this point, yeah. Okay? All right, yeah. So that is our first statement using this inversion concept. Another one, yeah. Then we improve it, and another version, if the array is not solid, okay, there must be an adjacent inversion. This time we add that adjacent property for the inversion. The first time we do not add adjacent. The second time we add adjacent. Two versions. Both statements are correct. Okay. And the second statement, the same as our, previous property we discovered. Okay. Yeah. All right. So here I write two different statements, but they are equivalent. Yeah. They are equivalent. Okay. One, I do not say an adjacent. I do not say an adjacent inversion. So we can refer the inversion as global inversion. Global inversion. Here, adjacent, adjacent, we can refer it to local inversion. All right, so global, local, right? Yeah, global, local. Which one is easier? Yeah. Remember when we did that greedy algorithm, we use that local, global views, right? Local view, global view. Here, we use this view another time. Local inversion, global inversion. Yeah. When we work on this particular problem, which way would be easier for us? Local view or global view? Local view, right? Local way easier. Yeah. Local way, every time you only consider two adjacent elements. Global view, you need to consider any two elements in the array. Yeah. Too many choices. Yeah. Local way, much fewer choices. Okay, yeah, the number of choices much fewer, yeah, much easier. All right, yeah. So here we take the local view, local inversion. All right, yeah, yeah. So I just say that. Okay, all right. How? So here the problem here, given an unordered array, we need to sort it, or we can say we need to fix the order problem. Right? So because our goal, we want to make this array in order, sorted in order. So we treat out of order behavior as a problem. So we want to fix the problem. Okay. How to fix the problem? We just want to fix an adjacent inversion. Think about that. Can we eliminate adjacent inversions? All the adjacent inversions we want to eliminate. That's the view. That's the special view for this new solution. Okay, think about that. All right. All right, so now how to fix it? Swap operation. Yeah. So you're familiar with swap operation, right? Swap the values of these two elements. Okay. When you do one swap operation on one inversion, can you fix it? Then it won't be inversion anymore, right? You swap two values for a pair of elements. If they form an inversion after the swap operation, there won't be an inversion, right? Yeah. So you eliminate one inversion in this way by the swap operation. Okay. Then after that, you can say we can eliminate all inversions using the swap operations. Okay. Yeah. Now the algorithm is pretty much there, almost there. Yeah. The main idea of this algorithm is there. Okay. Yeah. All right. So let me describe the implementation idea. All right. Remove all the local inversions by local swaps. you swap two adjacent elements. So that's the local swap operations, not global swap operations. Okay, all right. Yeah, so the procedure like this. You start from the first element for each scan. So you scan the whole array from left to right. All right. Do swap one by one from left to right, if necessary. Here you have to put this if necessary. Because if there is no inversion, you do not do any swap. So if necessary. Okay, only when you detect an inversion, then you do swap operation. Okay, all right, yeah, if necessary, yeah, I have it. Okay, stop at the first in-place element. What's the meaning of this third step? Stop at the first in-place element. You know the concept in place, right? Yeah. Because we need to do multiple scans. One scan won't get the whole array sorted, right? Think about it. One scan won't get the whole array sorted. Okay, yeah. So you have some out of order elements, one scan. But one scan, you can guarantee the last element is in place. Yeah. So when you do swap two other adjacent elements, eventually you can imagine you will put the maximum in place. Yeah. Put max in place. Right? So the next time you do not need to touch that max. You already put it in place. So you stop before you hit that max. So that's why stop at the first in-place element. Yeah. When you hit the first in-place element, you should stop. Okay, because they're already in place. Don't touch them. Okay, yeah. So that's the meaning of step number 3. Yeah. All right. All right. So now, then we have the whole solution. Yeah, yeah. So we observe the property for this solution. Yeah. There is one element in place for every scan. Every time we put at least one element in place. Okay. Yeah. Then after n-1 times, we put all elements in place. Right. Yeah. So the in-place element of each scan appears at the end of the current array. Yeah. At the end of current array. Okay. Yeah. Because we do local swaps. Okay. The largest element in the current array will be swapped to the end of the current array. And that is in place. Okay. Yeah. Then the current array is a subarray that excludes all the in-place elements. Yeah. Because you may ask me, what's the meaning of current array? Yeah. The meaning of current array, so the subarray of the original array, yeah, but that includes all the in-place elements. In place, we do not want to touch them. Okay. So we leave them alone. We do not want to touch them. Yeah. So that we only consider the current array. Okay. Then your scan on the current array, you will put the maximum of the current array at the end of the current array. So that is the behavior of this method. Okay. Yeah. So after the discussion, now we can get a visual imagination, visually, yeah, yeah. We understand visually, yeah. The swab looks like a bubble moving to the right, right? Yeah, moving bubbles from left to right. Yeah. So that's why people call bubble sort. Yeah. So that's why at the beginning I mentioned, you learned this before in CS2250, because the bubble sort appears in CS2250. Okay, bubble sort. Yeah. At that time, so you just did a simple algorithm, solve the problem. Okay, as a programming example at that time. Right. Here, we look at from the algorithm point of view. So this time, we learn more than the first time. Okay, yeah, all right. The efficiency analysis is similar to that of the selection sort. Yeah, you have n-1 scans, right? Selection sort, we have n-1 scans. Yeah. Each scan, we process subarray with one element fewer than the previous one. Yeah. Similar pattern. Yeah. So this one and the selection sort. Yeah. All right. So then the analysis pretty much the same. In selection sort, we did that analysis. Yeah. So here we can skip that because we just do the similar analysis as we did in the selection sort. Okay, all right. Then the question, what is the basic operation? We learned this concept. Basic operation, when we do the counting, we count the basic operation, right? Yeah. Here, there are two operations we can consider. One, comparison, right? In order to check if two adjacent elements form an inversion or not, you need to do a comparison, right? So comparison is one operation you need to consider. Another is swap operation, okay? Yeah. Comparison or swap, which one? Yeah. The answer is comparison, not swap. Why? Because you apply the comparison on all local pairs, adjacent pairs. Every time you take adjacent pair, you apply comparison operation. But you may not apply swap operation on adjacent pair. Because if you do not detect inversions, if they do not form inversions, so you do not apply swap operations. Yeah. So for that reason, comparison is more basic than swap. Okay? Yeah. Think about if your array is already sorted, then you won't need to do any swap operation, right? Already in order. You do not need to fix any inversion. There is no inversion in the array. So you do not need to apply any swap operation. Zero swap operation. Okay? Yeah. For that extreme case example, yeah. So you can understand comparison is more fundamental than the swap operation here. Okay, all right. So we spend a lot of time on this second solution, and we complete this topic. And we can treat it because here, although we use the inversion concept, because it's still quite basic, not advanced. So we can treat it, so this algorithm is still very close to brute force method. Okay, yeah. All right. Our second example for the brute force method, E.2, string matching problem. All right, string matching. So it's another simple computing problem, but this problem is very useful for string based search. Okay, keywords based search. Think about that. Keywords based search. Yeah. People use a lot keywords based search every day. Yeah. And there is some algorithm behind it. And here I just talk about the brute force method, because there is a much more advanced algorithm in our textbook, much more advanced. Yeah. All right, so here, mathematical representation. In order to solve this problem, string matching problem, you can guess, string matching problem, I will give you a description quickly. Yeah. But we need to use some mathematical representation on it. Okay. Problem number 5, string matching. Problem description. Given a string of n characters, a block of text, so we call it text, n characters, and a string of m characters, we call a pattern. And we assume m less than or equal to n. The pattern, we mean a keyword, smaller string keyword. Yeah. So m with m characters. So find a substring in the text that matches the pattern. That's the problem. String matching problem. Okay, yeah. Here, the brute force method, I guess everybody can apply the brute force method to find a solution. Okay, yeah. Here, we do discussion. But we need to work on the mathematical representation first. All right. Yeah. So the solution means you need to find the location of the pattern, the substring that corresponds to, that matches the pattern. Okay, yeah, location. Yeah. All right. Yeah. But for the location, you need to interpret what is the exact meaning of the location. Here, the meaning is the index I of the leftmost character, not the rightmost, not anyone in the middle, just the leftmost index I. Okay, yeah, all right. Yeah. First solution. Straightforward thinking. We do not need to use any fancy method, just straightforward, based on our intuition. Okay, so we do the comparison, substring comparison, one after another. Okay. But we cannot do it mentally, so we need to write out the expressions, specific expressions first. Okay, write down on the paper, so then we can see the expressions clearly. Okay, not mentally, yeah. On paper clearly. Okay, yeah, all right. Because if we have mathematical representation, then we can apply mathematical tools. Okay, so we may have some formulas, some special methods. Yeah. If we do not have the mathematical representation, then it's not convenient to apply any mathematical tool. Okay, yeah, all right. Text, what is the mathematical representation for the given block of text? A sequence of characters, right? And also, we need to mark the location information for each character in the text. Yeah, so here we use this way. T, because text, each character in the text, we use little t, and the location information, we use subscripts. The index of each character in the character array. Yeah, we can treat it as a character array. Okay, yeah. With indices from 0 through n-1. That is the first representation. Second, the pattern. We use P. Yeah. So P sequence, character sequence. Yeah. And with indices from 0 through n-1. Yeah. With these two expressions, then we can do discussions. We can write detailed discussions clearly on paper. Okay? Yeah. Not in our mind. In our mind, we will get lost quickly, right? Yeah. So we will get lost. Yeah. So we need to write it on paper. Yeah. All right. Requirement. Find the location. What do you mean find the location? Find the location I. Yeah. So let's describe a typical matching case. Matching, substring matching case. Yeah. I such that T sub I equals P sub 0. Yeah. P, the first character in the pattern, matches the substring, yeah, whose first character is at location I. All right, yeah. Then T sub I plus J, yeah. So you move position to the right. So I plus J. I plus J means you move J positions to its right. All right, yeah. So this one usually a little harder for some students to understand. Yeah. All right. So you move the pointer. Yeah. All right. Move the pointer. Yeah. Okay. To the right. Yeah. In T sequence, if you move the pointer one position to the right, so in the P sequence, you also need to move the pointer from one position to the right. At a T position, you move to J positions to the right, and P sequence also J position to the right. Okay, yeah. One by one, one-to-one correspondence, all matching, yeah, until you reach the last character of each sequence. Okay, yeah. The last one, T sub I plus n minus 1 equals P sub n minus 1. Okay, that's the expression. Think about that. If you can understand this sequence of expressions for a matching case. So that's the matching case. Okay, it's a matching case. That's the matching case. Okay, all right. Here's the strategy. Here, guess and verify strategy. Yeah, because in order to solve this problem, yeah, although it's a simple problem, but in order to find a solution, in order to, get a correct formula, here we use the guess and verify strategy. Yeah. All right, so let me describe it. Yeah. Thinking. Yeah. Let us do the thinking here. All right. Question. Can we exhaust all such M substrings? Now, when you do the matching, if we can exhaust all M substrings in the given text, then we can complete all possible comparisons. We can make all possible comparisons. So here we need to answer this question first. We have finite many characters in a given text, finite many, so we can exhaust. That's easy. Moving from left to right, because we only, every time we only look at M adjacent, M consecutive characters. So we can easily exhaust all substrings containing M consecutive characters. Okay, yeah, all right. Yeah. So to get a step-by-step procedure, step one, every time we extract one M substring from the text with consecutive characters. Okay. Every time we just take out one M substring, yeah, with consecutive characters. Okay. Step two, compare it with the pattern for a possible match. Yeah. All right. So this kind of comparisons, one after another, in order. Okay. Yeah. Then another question. How many such M substrings? How many M substrings do we need in order to exhaust all possible substrings, M substrings? Okay, there must be some number there, right? And it should not be that hard to find that number. Okay, yeah. But here, I like to introduce some method. Things like this is pretty easy, yeah, but I like to introduce some useful method for you to find the answer. Okay, all right. Yeah. So before we apply that method, so here, yeah, because guess and verify strategy, in order to get this answer, guess and verify strategy, yeah, how many M substrings? Yeah. All right. So you may need to imagine. All right. So suppose this is the text. Okay. Yeah. You know, with N characters, the length is N. Length is N. All right. Length is N. Then the pattern usually smaller, right? Pattern. Okay. Pattern much smaller than the text. You know, the length is N. Okay. Yeah. All right. So the first substring, when you start from the left, you take M consecutive characters from the leftmost point to get started. Then every time you move one position to the right, yeah, until you reach the last M consecutive characters, N, length N, all right? Yeah. And how many different steps you can move to reach the last M substring. Okay, yeah. Here, guess first. An obvious guess, M minus M, right? Yeah, because based on our intuition, right? Yeah. But your guess may not be correct. You need to verify it. Yeah. Guess, then you need to verify it. Your guess may not be correct. Okay. Yeah. Many times it's not correct. We need to fix it. Okay. Yeah. How to verify it? Yeah. Here, a simple way. Try to find some simple case. You can find the answer easily. Yeah. So what's the simple case? Extremal case where m equals n. That's the one extremal case. The pattern and the text, they have the same length. When they have the same length, the answer is 1, right? So there is one m substring in the pattern, only one, not 0. Yeah. But this n minus 1 gives you 0, right? Yeah, your guess is not correct. Your guess is 1 away from the true answer, or 1 less than the true answer. So you need to do the adjustment. You need to add 1 on top of your guess to get a correct answer. So then you fix it. So the correct answer should be n minus m plus 1 to fix it. Okay, to fix it. So in this way, so this is a simple method, guess and verify strategy, but you try it on a simple example, so you can handle easily on that simple case. Yeah. So here you get the idea. Okay, guess verify idea. Okay. All right. Now, next one, we need to count the number of comparisons. We need to count the number of comparisons. Okay, although it's not hard, okay, yeah. Actually, it's pretty straightforward, yeah, pretty straightforward to count. How many character comparisons you need to do here? Okay, yeah. Implementation details. We need, when we do implementation details, yeah. So we need to do a for loop, right? We need to run a for loop for the character comparisons. All right. So when we do a for loop here, let us apply for loop on the sequence of characters in the given text, yeah, here in this diagram. All right. And we start in our for loop, we start from the first m substring. Yeah. Then when we start, the position number, yeah, the subscript of the first character equals 0. So the position, location of this m substring is 0. All right, yeah. Then when we reach the end of the last m substring in the given text, so we need to figure out the location of the last m substring. So that question mark. So at this point, we may not be able to guess correctly. So what should be the correct location of the last m substring? Okay, we need to figure that out. After we figure that out, then we can write that for loop easily. Okay, yeah. But this question mark still, it's a small problem, but we need to solve it first. Okay, yeah, here. The question, how to solve this problem? The question, how to figure out the subscript? If you just guess, how do you know your guess is correct? Right? How do you know your guess is correct? You need to find a way to verify it. Verify your guess. Okay, yeah, all right. So you can apply our previous strategy, the strategy from our previous slide. But here, I like to introduce another problem-solving thinking method. So very useful thinking method. I like to introduce that one. Yeah. Because later we will use this method a few more times. Yeah. All right. But today we do not have that much time to talk about this method. Yeah. I will leave this method next time. Yeah. Next time we will start module 3, but at the beginning of the module 3, I will spend about 10 minutes to complete this method. Yeah. This important method. Okay. All right. I like to stop right here, and